In our previous lessons, we discussed the fact that power series can be thought of as functions whose domain is the set of all x for which they converge. You might be thinking, well, so what? They're functions, what does that matter? But it turns out we can actually find power series representations of functions that are sort of common functions that we know, and these in turn can be used to estimate and approximate functions. So today we're going to actually talk about what kinds of functions those power series representations can be equal to. So today we're going to find power series representations for a variety of functions, and most of the series we handle today are going to use the sum of a geometric series in some way or another. So we're going to need to remember that the sum of from n equals 0 to infinity of a r to the n, the geometric series, is equal to a over 1 minus r if the absolute value of r is less than 1. So, and that's what it converges when the absolute value of r is less than 1, and diverges if r is bigger than or equal to 1, or if r's absolute value is bigger than or equal to 1. Now what we're going to do is we're going to use this formula backwards. So here is the simplest case. I have the function f of x that is 1 over 1 minus x. Think a over 1 minus r. Now if you think about it this way, you see that the a is equal to 1, the r is equal to x. So this function can be thought of as a series, a sum from n equals 0 to infinity, a r to the n, where that is the a and that is the r. So sum from n equals 0 to infinity, 1 times x to the n, or a sum from n equals 0 to infinity, x to the n. And this will converge if the absolute value of r is less than 1, or the absolute value of x is less than 1, which is the same thing as saying negative 1 less than x less than 1. We don't need to test x equals negative 1 and 1 because we use the fact that it's a geometric series, and the geometric series will diverge when x is negative 1 and 1. So what this tells us is that the function 1 over 1 minus x is equal to, well, 1 plus x squared plus x cubed, etc., so long as the absolute value of x is less than 1. So if you felt like you wanted to convince yourself that this is true, what you could do is you could graph this 1 over 1 minus x function, and you can graph partial sums of this, and notice that as you add more and more terms, the partial sums are converging to this function 1 over 1 minus x on this interval. Oops, not or equal to, just less than. So negative 1 less than x, which is less than 1. Okay, and you say, okay, well, that's a really simple case. Let's talk about how we can sort of generalize that to a little bit more complicated case. So here I have 1 over 1 plus x to the 5th. So the goal is to make this look like a over 1 minus r. So well, you say, well, I can make that into 1 over 1 minus negative x to the 5th. That's the same thing. And at that stage, your a is 1, and your r is negative x to the 5th. So this is equal to the sum from n equals 0 to infinity, 1 times negative x to the 5th to the n. And I want you to simplify that into negative 1 to the n, x to the 5n, using exponent rules. And this will converge if the absolute value of negative x to the 5th is less than 1, which says x to the 5th has to be less than 1, and that means that x has to be between negative 1 and 1 once again. Alright, so that's not so hard, so the whole use a double negative so you have a minus sign. Now what if this number had not been a 1? How we deal with that? And here is an example. So we have 2 over 3 minus x. So to deal with the fact that this is not a 1, divide the numerator by 3 and the denominator by 3. That means we can express f of x as 2/3 over 1 minus x over 3. And now you can see it's in that a 1 minus r form. The a will be 2/3, the r will be x over 3. So this is the same thing as the sum from n equals 0 to infinity, 2/3 times x over 3 to the n, which is the same thing as the sum from n equals 0 to infinity, 2/3 times x to the n over 3 to the n. And notice you can express that denominator as 3 to the n plus 1. So 2x to the n over 3 to the n plus 1. And this is the first example where our radius of convergence is not going to be 1. This will converge if the absolute value of x over 3 is less than 1, which is the same thing as saying the absolute value of x is less than 3, or negative 3 is less than x, which is less than 3. All right, now this one will have some sort of combination of those two things put together. So, okay, so first of all, let's think about this. I'm going to think about this as x to the third times 1 over 81 plus x to the fourth. I'm going to divide out that 81. So I will have x to the third times 1 over 81 over 1 plus x to the fourth over 81. And so one more step, let's think about that as x to the third times 1 over 81 over 1 minus negative x to the fourth over 81. Okay, now this is of that geometric series form, a over 1 minus r, and the a will equal 1/81st, and the r will equal negative x to the fourth over 81. So you have x to the third times the sum from n equals 0 to infinity, 1 over 81, times negative x to the fourth over 81 all to the n. And simplifying that slightly, we have the sum from n equals 0 to infinity, negative 1 to the n, x to the 4n, and 81 will be raised to the power of n plus 1. Now the question is, what do you do with this x to the third? Well, that's kind of just like a constant, so it can multiply in. And when you multiply x to the third times x to the 4n, those exponents add, giving you x to the 4n plus 3. So this will be the same thing as the sum from n equals 0 to infinity, negative 1 to the n, x to the 4n plus 3, over 81 to the n plus 1. All right, this series will converge if the absolute value of negative x to the fourth over 81 is less than 1. Same thing as saying x to the fourth has to be less than 81. And that will be true if x is in between negative 3 and 3. All right, next let's find a power series representation for this function, x plus a over x squared plus a squared. Well, the first thing that you have to do is you're going to have to break f of x up into two pieces. Let's write it as x over x squared plus a squared plus a over x squared plus a squared. So we're going to find power series for both of those. Let's call them number 1 and number 2, and then add the results together. So first for number 1, we have x over, I'm going to write it as a squared plus x squared. So first I have to make this a squared into a 1, which I will do by dividing by a squared. So I will have x over a squared over 1 plus x squared over a squared. Now the next thing is that needs to be a minus, so let's write that as x over a squared over 1 minus negative x squared over a squared. So that will be a sum from n equals 0 to infinity. X over a squared, that's my a, negative x squared over a squared to the n. So that will be the same thing as the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, over a to the 2n plus 2. So that's for number 1. Number 2 is actually a little bit simpler. We have a over x squared plus a squared. So first let's divide out that a squared of a over a squared over 1 plus x squared over a squared. Same thing as 1 over a over 1 minus negative x squared over a squared. So that's the sum from n equals 0 to infinity, 1 over a times negative x squared over a squared to the n, or the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n over a to the 2n plus 1. And so now combining those results, we have f of x is equal to a sum of these two things. So it's the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over a to the 2n plus 2, plus negative 1 to the n, x to the 2n over a to the 2n plus 1. You can simplify this slightly by factoring out the greatest common factors. So obviously there's a negative 1 to the n in common. There's an x to the 2n in common as well. And there's also an a to the 2n plus 1 in common. When you factor that out, you're left with x over a plus 1. So there is your final answer. If you want to convince yourself that that's correct, you can just redistribute that, and you should see that the powers all match up as they should. Now, to look at the radius of convergence, we have to check it out both at this stage and at that stage. Notice that in both of those cases, the r is the same thing. So this will converge so long as the absolute value of x squared over a squared negative is less than 1, which is the same thing as saying that x squared must be less than a squared, or x is between negative a and positive a. Now we're going to use a similar idea to express this function as the sum of a power series by first using partial fractions. We use partial fractions to break this up into two functions that we can use geometric series to find power series of those, and then we'll add them together. The radius of convergence here will be a little bit different than the previous one because the r's used in these two cases will be different. So first, partial fractions. So we're going to break 2x plus 3 over, so factor that denominator, that's x plus 1 times x plus 2. That will be a over x plus 1 plus b over x plus 2. Same thing as saying 2x plus 3 equals a times x plus 2 plus b times x minus x plus 1. Now subbing in x equals negative 2, we find that negative 4 plus 3 will equal negative b. Negative 1 equals negative b, therefore b is positive 1. If we sub in x equals negative 1, we have, well, negative 2 plus 3 equals a, so a is also equal to 1. So we now can express f of x as 1 over x plus 1 plus 1 over 2 plus x. So there's our first partial fraction step. Now, once again, let's call this first one number 1, let's call this second one number 2, and let's find power series representations for both of them separately. I think I'm going to need a new slide, so let's add one in. Okay, so number 1, that's 1 over 1 plus x. That one's pretty simple. 1 over 1 minus negative x. That will be the sum from n equals 0 to infinity, 1 times negative x to the n, or the sum from n equals 0 to infinity, negative 1 to the n, x to the n. Notice this will converge if the absolute value of negative x is less than 1, which is the same thing as saying absolute value of x is less than 1, or x is between negative 1 and positive 1. Number 2 is a little bit more complicated, but not a lot. First we have to divide by 2, so we'll have 1/2 over 1 plus x over 2, or 1/2 over 1 minus negative x over 2. That's the sum from n equals 0 to infinity, 1/2 times negative x over 2 to the n, which is the sum from n equals 0 to infinity, negative 1 to the n, x to the n, over 2 to the n plus 1. And this will converge if the absolute value of negative x over 2 is less than 1, or absolute value of x is less than 2, which means x is between negative 2 and positive 2. Okay, first let's get an expression for the power series representation for f of x, and then we'll talk about its radius of convergence. So f of x is the sum of number 1 and number 2. So we have the sum from n equals 0 to infinity, negative 1 to the n, x to the n, plus negative 1 to the n, x to the n over 2 to the n plus 1. All that stuff. I just care that you can factor out the greatest common factor to simplify that slightly. So that's the sum from n equals 0 to infinity, negative 1 to the n, x to the n, multiplied by the quantity 1 plus 1 over 2 to the n plus 1. Now this will converge if you have x satisfies both it's between negative 1 and 1 and negative 2 and 2. So the x's that satisfy both those inequalities means this will converge if x is between negative 1 and 1. There are some values for which this second series converges that first series does not. But for this series for f of x to converge, both individual components of it must converge. So that's where the restriction comes from. You look at the restrictions for your two individual series that are summed, and you do what's called take the intersection of the two. All right, another method we will have to find power series is using differentiation and integration. So the sum of a power series is a function f of x whose domain is the set of all x for which f of x converges. And we want to be able to differentiate and integrate these functions. And the following theorem says we can do so just by integrating or differentiating on a term-by-term basis, just like we do for polynomials. So for example, if you have f of x is 1 plus 2x plus 3x to the second plus x to the fourth, you know that f prime is 0 plus 2 plus 6x plus 4x cubed. You can differentiate each individual term separately. You also know that the antiderivative of f of x is x plus 2x squared over 2 plus 3x squared over 3 plus x to the 5th over 5 plus some constant c. The point being, you can integrate each term individually, and that is how you integrate polynomials. Turns out you can do that for infinite series as well. So if the power series has radius of convergence r that's bigger than 0, then this function is differentiable and continuous on the interval a minus r, a plus r. This time, I'm sorry, I just transpose those. We've usually been using a's for those and c's for those, but it doesn't matter. So anyway, if you differentiate this thing, let's do it on a term-by-term basis and look at what happens. C0 is a constant. Its derivative is 0. The derivative of C1 times x minus a, you can think about that as C1x plus minus C1a. Well, the derivative of that C1a is going to be 0, so the derivative there will just be C1. Next, we'll have 2c2 times x minus a. The next term we would have added in there would be c3 times x minus a to the 3rd. So we'll have plus 3c3 x minus a to the 2nd. And you can see there you get some kind of pattern there. So first thing to notice is that the coefficient matches the numberth term. The second thing to notice is that the power is 1 less than that coefficient. So if we're going to express this in sum notation, again, this is the sum. We're going to start this sum at 1 because our 0th term is gone. So we'll have Cn times n x minus a to the n minus 1. And notice what happened is just this part was treated as if it was being differentiated. These Cn's are constants. They stayed the same. The derivative of x minus a to the n will be n x minus a to the n minus 1. So the thing that gets differentiated is the thing that has the x's in it. Now if we integrate, the antiderivative of c0 will be c0. I'm going to fuss a little bit, and I'm going to say times x minus a. We'll talk a little bit in a second about why that's okay that I do that. The antiderivative of c1, x times x minus a, will be c1 over 2 x minus a squared, then plus c2 over 3 x minus a cubed. There'll be plus some overarching constant c that's getting added on. And the reason that I can make that c0 times x minus a instead of just c0 times x is the fact that I have this additional constant c0 times a can kind of be compensated for in what this plus c will be. So that's why you can do that. So it seems like a little bit like magical, but since that plus c is not determined, you can kind of add constants in two different places. Okay, once again, this sum will start at 0 because we have that 0th term. We'll have c0. Now, notice that you have c0 over n plus 1. So c1's over 2, c2's over 3, times x minus a to the n plus first power, plus some constant c that is added on at the end of the series. And notice once again, all you did was integrate this stuff to the n. The antiderivative of x minus a to the n is x minus a to the n plus 1 over n plus 1. And the great thing here is that the radii of convergence of the power series obtained by differentiation and integration are the same as the original, but convergence may differ at the endpoints. So what this means is if you know R for the original, you just need to retest the n's. Don't go ahead and do the whole ratio test again. All you need to do is retest the endpoints. All right, let's actually just differentiate a function, then we'll talk about how we can find a power series representation of a function. So the trickiest thing here is figuring out what the variables are. So everything that has an n is a constant, and it has an n and has no x. So that's -1 to the n, 2 to the 2n, n factorial squared. That's all the constants. X to the 2n, that's the thing that is being differentiated. So when you take the derivative, you start your series at 1 now because your 0th term is gone. The constants get left alone, just like they do with constants for regular differentiation. The derivative of x to the 2n will be 2n times x to the 2n minus 1. And so that will be the sum from n equals 1 to infinity, -1 to the n, 2n, times x to the 2n minus 1, all over 2 to the 2n, times n factorial squared. But the point there being the thing you differentiate is the thing that has the x. Everything else is a constant. So express f of x as a power series using differentiation. So what we're going to start by observing is if we anti-differentiate this thing, it will tell us what we have to differentiate to get it. So that's the same thing as the integral of 1 minus x, the quantity to the -2nd, which applying the reverse chain rule is 1 minus x to the -1st over -1 with an additional -1 factor because of the -x, plus some constant c, or it's 1 over 1 minus x plus c. So what this means is that the derivative of 1 over 1 minus x will equal 1 over 1 minus x squared. So if we take the derivative of this series, we're going to get that one. Okay, so we're going to find the derivative of 1 over 1 minus x's series. And you have to integrate to figure out what you're going to find the derivative of. So that's the derivative of the sum from n equals 0 to infinity, x to the n. And using our term-by-term differentiation, we can say this is a sum from n equals 1 to infinity, n, x to the n minus 1. And that is the power series representation for 1 over 1 minus x, the quantity squared. Now we know from earlier the radius of convergence for 1 over 1 minus x is 1. So we know that r is 1. We know that we have convergence if the absolute value of x is less than 1, or -1 is less than x, which is less than 1. We just need to retest x equals -1 and x equals +1. So at x equals -1, we have the sum from n equals 1 to infinity, n times -1 to the n minus 1. And at x equals 1, we have the sum from n equals 1 to infinity of just n. Both of those diverge. D-I-V-E-R-G-E. There you go, by the test for divergence. So the interval of convergence here is -1 less than x, which is less than 1. Now, the trickiest thing is just figuring out, keeping your integrals and derivatives sort of straight, and figuring out what to integrate or differentiate. All right, let's do an example where we have to actually use an integral instead. So find the power series representation for ln of 1 minus x. And you think to yourself, the derivative of ln of 1 minus x, well, that's 1 over 1 minus x times negative 1, so negative 1 over 1 minus x, and thus the integral of negative 1 over 1 minus x is going to equal ln of 1 minus x. So you say, well, ln of 1 minus x is equal to the antiderivative of negative 1 over 1 minus x, and you can find a power series representation for that guy. So that's the same thing as the integral of the sum from n equals 0 to infinity, negative 1 times x to the n, or it's the sum from n equals 0 to infinity. The negative 1's a constant. When you anti-differentiate x to the n, we get x to the power of n plus 1 over n plus 1, and then plus some constant c. Now we need to figure out what that c is. How you can do that is you can plug in a value for x. I suggest plugging in x equals 0. Think for a second about why I think x equals 0 is a good thing to plug in. Okay, gave a few seconds. When you plug x equals 0 in, that zeroes out the entire sum. And we'll have ln of 1 equals c, which means that in this case, c is actually equal to 0. So we have a power series representation for that function, ln of 1 minus x, is the sum from n equals 0 to infinity, negative 1 x to the n plus 1 over n plus 1. Now we need to find its radius of convergence. Let's do one better and actually find the interval of convergence. We know from this step right here that that series will converge if the absolute value of x is less than 1, which means negative 1 is less than x, which is less than 1. We just need to retest the endpoints. That theorem that we had, which we did not prove and will not prove, says that the radius of convergence for a series and the integral of that series are the same. So at x equals negative 1, we have the sum from n equals 0 to infinity, negative 1 times negative 1 to the n plus 1 over n plus 1. Well, that's going to become the same thing as negative 1 to the n plus 2 over n plus 1, and that will still alternate. So this would converge by the AST. At x equals 1, we have the sum from n equals 0 to infinity, negative 1 over n plus 1. And since that numerator is just negative 1, not negative 1 to the n, this is going to diverge. It's just negative 1 times basically the harmonic series. So the interval of convergence here includes negative 1, but does not include positive 1. All right, and another sort of common example is a power series for arctan. So notice that the derivative of arctan, because integrating that sounds like very much not fun. Let's just hope we can differentiate and get something useful. The derivative of arctan is 1 over 1 plus x squared. So that tells you that arctan is equal to the integral of 1 over 1 plus x squared. And you can actually find a power series for this 1 over 1 plus x squared. That's the same thing as 1 over 1 minus negative x squared, which is the same thing as the sum from 0 to infinity, negative x squared to the n, or the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n. Now the antiderivative of x to the 2n will be x to the 2n plus 1 over 2n plus 1. So our power series representation for arctan is the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 plus some constant c. And you do the trick where you plug in x equals 0 again, you get arctan of 0 equals your c, and arctangent of 0, well, that's 0. So we have that arctan x is equal to the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Now we need to find the interval of convergence. The directions don't say it, but you're going to have to for a problem you do, so I'm just going to go ahead and do that. So at this stage where we used a geometric series, we know we converge if the absolute value of negative x squared is less than 1, which means that x is between negative 1 and positive 1. We just need to check those endpoints. So at x equals negative 1, we have the sum from n equals 0 to infinity, negative 1 to the n, negative 1 to the 2n plus 1, all over 2n plus 1. Well, those exponents add, and we have the sum from n equals 0 to infinity, negative 1 to the 3n plus 1 over 2n plus 1. And you can verify for yourself, but this series still alternates. When you plug in 0, you have negative 1 to the first. When you plug in 1, you have negative 1 to the fourth. You plug in 2, negative 1 to the seventh. The numerator will indeed flip-flop. So this will converge by the alternating series test. And at x equals 1, it's even easier. We have the sum from n equals 0 to infinity, negative 1 to the n over 2n plus 1. And that will also converge by the AST. So your interval of convergence here includes both negative 1 and positive 1. Now we can use the power series that we found earlier to find power series for functions that are related. So note that you know that the power series for ln of 1 minus x is the sum from n equals 0 to infinity, negative 1 x to the n plus 1 over n plus 1. And this will construe if the absolute value of x is less than 1, or specifically x is between negative 1 and positive 1. And at negative 1 it did also converge. But we're just going to focus on finding the power series. So we can take f of x, which is natural log of 1 plus x squared. We can write that as ln of 1 minus negative x squared. And we can plug this negative x squared in for the x. So a power series representation there is a sum from n equals 0 to infinity, negative 1 times negative x squared to the n plus 1, all over n plus 1, or a sum from n equals 0 to infinity, negative 1 times negative 1 to the n plus 1, x to the 2n plus 2, because those exponents multiply, over n plus 1. Or that's the sum from n equals 0 to infinity, negative 1 to the n plus 2, x to the 2n plus 2, all over n plus 1. Or the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 2 over n plus 1. So all that occurred there is I took this negative 1 to the n plus 2 and said, oh, that's the same thing as negative 1 to the n times negative 1 to the second, and negative 1 to the second is just 1. You don't have to do that, but it does make it more obvious that your series is alternating, so I think it's a good idea to do that. And similarly, let's use arctan. So we know that the formula for the power series for arctan, or tan inverse of x, is the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. So for g of x, which is inverse tangent of 5x, we just plug in 5x for the x. Notice that this means that both the 5 and the x are raised to the 2n plus 1 power. So I'd like you to express that with the power sort of distributed to both pieces. So negative 1 to the n, 5 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1. So that's another way you can use power series that you know to get power series for functions that are closely related.